Good morning. My name is Han Xinyi, and I'm a second-year PhD student. I have the same project with the last speaker. I also work on the aneurysm. And today I will make a presentation named Hemodynamic Effect of Aortic arch presence upstream from healthy aorta and abdominal aortic aneurysm. And I will follow this section to introduce my work. The first part is the objective and the background of this project to introduce the current state of aneurysm simulation. Secondly, around the arch effect objective, I performed the hemodynamic comparison study of simulation with and without arch in healthy aorta and aneurysm, and I will present the simulation detail later. Finally, I will finish my report with the conclusion. The first question is, what is the aneurysm? The aneurysm is an abnormal dilation in human aorta and is a common disease for elder individuals because of the vascular elasticity reduction and the continuous shear stress at vessel wall because of the high mortality after rupture. The development and the rupture of aneurysm are severe threat for human health. Therefore, it's necessary to analyze the flow state in the aneurysm to clear the generation of aneurysm and predict the risk of development and rupture. Currently, the simulation geometry of aneurysm is mainly divided into two types. The first one is the entire model from ascending aorta to iliac artery, and the second one is only focused on the aneurysm domain. Because of the arch curvature and the cross flow inside the arch region, most people prefer to use the simplified model to make the simulation, which can shorten the calculation time. On the other hand, some studies ignore the arch effect because the distance of aneurysm is far away from the arch. But now the difference and the comparison study of these two type of geometry are not clear. Therefore, it's important to explore whether the arch curvature, cross flow, and the distance has effect on the flow state in the aneurysm. In order to clear the arch effect on flow state in the aneurysm, I selected the healthy descending aorta as the study domain and made the first simulation. And now I will start to introduce the simulation of arch and archless descending aorta model. On the left figure is the geometry of arch aorta model with 1 inlet and 5 outlet. The archless model is cutting from the arch model, and the cutting surface is selected at the position with curvature is close to 0. And the mesh is created with snappy hex utility in open form. Figure 1 is the mesh independence study of different mesh number and the inflation layers. The average wall shear stress value in arch descending aorta tend to converge after 1.3 million with 2 inflation layers. And then I use this model to make my follow simulations. And the mesh distribution is shown in the figure. The boundary condition is unimportant. The boundary is an important part of aorta simulation. In order to conform with the actual aorta, the boundary condition is calculated with 3-element wind cancel model. And the wind cancel model uses the elastic circuit model to simplify the behavior of aorta. The compliance is defined as the elasticity of vessel wall, and the pressure from heart and posterior is considered with the resistance. And the resistance and the comparison of branch aorta are related with the outlet area size and the flow rate of each aorta. And then the outlet pressure boundary condition is calculated with wind cancel equation with the different resistance and compliance parameters, which is shown in figure 3. For the inlet boundary condition, I use the human clinical flow rate shown with the black line in figure 2. In the ARCH simulation, the output flow rate at a cutting surface is defined as the ARCH-less inlet boundary condition. Firstly, I analyzed the ARCH effect on velocity field in healthy aorta and plot the curve of velocity with diameters at 3 different moments at the systolic peak, transition point, and the diastolic peak. The black line are the velocity curve in ARCH model, and the red line are in the ARCH-less model. The velocity curve are in good agreement at systolic peak in ARCH and ARCH-less model. And the specific velocity field are shown in the right figure to investigate the ARCH effect on the velocity distribution. The figure reveals the velocity field at A, B, C location in ARCH and ARCH-less model at transition point and the diastolic peak. In this figure, we can understand the position of maximum velocity is similar. The difference of both models is occurred at the center of vessel because of the ARCH curvature. The irregular flow generated from the ARCH deviated the flow direction and increased the irregular flow at the center of descending aorta domain. Secondly, the time average wall shear stress distribution for ARCH and ARCH-less model are shown in figure 6. At this model, at this figure, we can understand the value and the distribution of time average wall shear stress are similar in both models. And the region and the low time average wall shear stress is prone to thrombosis. The low time average wall shear stress percentage are 5% in ARCH model and 7% in ARCH-less model. And both model with a low risk of thrombosis. In short, the ARCH effect in healthy descending aorta is occurred at the central velocity distribution, and the relative different value of time average wall shear stress is 16%. And now I have finished the simulation result in healthy aorta, and I will talk about the simulation in aneurysm model. In the same way, I make the comparison hemodynamic study of aneurysm with and without ARCH. The geometry of aneurysm model is shown in figure 8 with 1 inlet and 9 outlets. The ARCH-less model is obtained from the cutting surface, and I use the human clinical flow rate as the inlet boundary condition shown in black line. And the flow rate at cutting surface is defined as the ARCH-less inlet boundary condition. The outlet pressure is taken into account the elasticity wall and the resistance from heart and posterior artery, calculated with wind cancel model shown in figure 11. The time average wall shear stress was calculated to investigate the risk of thrombosis and growth in aneurysm. The time average wall shear stress distribution of ARCH and the ARCH-less model are shown in figure 12. The figure indicated the distribution of time average wall shear stress are similar in both models, but at the arch aneurysm sank, the value of time average wall shear stress is lower than the archless model. The region of time average wall shear stress below 0.4 Pascal is prone to thrombosis. The low time average wall shear stress distribution is also shown in the figure, and the region of low time average wall shear stress percentage are 21% in arch model and 19% in archless model. And the last red value and the figure in red box are the verification from the reference literature. The thrombosis is prone to occur in the middle of sank and around the aneurysm neck, with the same result with the reference literature. In order to understand the reason of low time average wall shear stress distribution, I analyzed the vorticity distribution in aneurysm sunk at 1.43 seconds in arch and archless model. The arrow indicated the direction of velocity. The main difference in vorticity distribution is occurred around the neck and the maximum diameter of sunk. In the arch aneurysm model, because of the arch effect, the blood flow from the arch increased the irregular flow around the neck and moved the vorticity far away from the vessel wall. But in the archless model, because of the inlet uniform velocity flow directly to the vessel wall, which will increase the friction between the blood and the vessel wall. The high vorticity is close to the vessel wall and lead to the high wall shear stress. In short, the arch increase the irregular flow and make the vorticity move the center. In conclusion, for the simulation in aorta with arch model, the arch region will increase the irregular velocity distribution and enhance the degree of disturbance. And the second point, the blood flow deviated to the vessel center due to the curvature of aortic arch. And for the simulation in aorta without arch model, because of the uniform inlet velocity, the blood flow directly to the vessel wall, which will increase the wall shear stress, and underestimated the risk of thrombosis and the development in abdominal aortic aneurysm. So the simulation result indicated that the arch and archless influence on the blood flow state is not negligible. In order to evaluate the blood flow inside the abdominal aortic aneurysm, the arch aorta model should be used for experiment and simulation study. This is my presentation. Thank you.
All right, let's thank our speaker.